Hello, it's Dr. Daystorms. And in the second lecture in this series of this chapter, we're going to be talking about the transfer of energy and how, like mass, when we have the law of conservation of mass, we have the law of conservation of energy, where energy is neither created nor destroyed. And so, for this example here, we have this lump of clay, this clay ball that's setting on top of a wall that's a certain height above the ground. So it has a certain amount of potential energy. Then, as that ball starts to fall, its potential energy is being converted to kinetic energy. Okay, just like that's an example from the last video. We talked about a man bowling with a bowling ball and how the potential energy was converted to the kinetic energy as he bowled the ball. However, now what happens whenever this clay ball hits the ground? Its kinetic energy now is zero because it's no longer moving. However, we can't just say that energy disappeared. So what happens is that energy does work on the ball because the ball becomes smashed, and the rest of it is actually given off as heat. And so the heat then flows from the ball to the ground below. So let's look at a funny example of this. So in this example, we're going to be doing skateboarding again. However, now the skateboarder no longer is going to be skating. He's going to fall. So at the top of the ramp, he has the highest amount of potential energy. Kinetic energy is now down to zero because it does work on his body. And at the same time, he's giving off heat to the ground below. Oh my goodness. So the first law of thermodynamics states that energy is neither created nor destroyed. Okay? So, in other words, the total energy of the universe, remember we talked about the universe being the system and the surroundings, is constant. If the system loses energy, it must be gained by the surroundings, either in the form of heat and or work. And vice versa. So therefore, if the system gains energy, that means the surroundings lost that energy. And so this is just an example here where we have the total amount of energy for the universe. And please note, some books, including yours, uses a U for internal energy rather than an E. However, most of the figures that you will see will use the letter E instead of U. So the total amount of energy in the initial is actually greater than in the final. So it's much lower because the system lost the energy to the surroundings. It gave it off in the form of either heat or work. The opposite can also be true, where the system actually gets energy from the surroundings. Okay, now your book likes to use the letter U for internal energy, but many diagrams that you'll see will actually have the letter E. So we're going to be using them interchangeably in this chapter. So the internal energy of a system is going to be the sum of all the kinetic and potential energies of all the components of that system. So once again, we're going to be calling it U. This is very important. Many equations, I'm going to give you the equations, but I will never give you the delta equations here because it's very simple. Delta U is going to be equal to the final U minus initial U. Or you can think of it as the change in energy is equal to the final amount of energy minus the initial amount of energy. Okay, if U is positive, it means that the system gained the energy from its surroundings. This is very important because that's called an endergonic system. So delta U is positive, or delta E would be positive. It's going to be greater than zero. The opposite is whenever the system loses the energy and it's going to release it to its surroundings. Now the delta E, or the delta U in our case, is going to be negative, and it's called exergonic. Endergonic is positive, greater than 0. Exergonic is negative or less than 0. Okay. Whenever we're talking about energy being either gained or lost, it has to be done so in either the form of heat, which is a Q, or work, which is W. And so these are the two terms that we've been using. Okay, so this instance here, this example here, the surroundings is giving heat to the system, or the surroundings is doing work on the system. Both instances is positive, and so the delta E or the delta U is going to be greater than 0. So you can figure this equation. Delta U is going to be equal to the amount of heat plus the amount of work. Please note, you can actually have heat lost but work being done on the system. So the sign of Q, W, and delta U are all very, very important. So what do I mean by that? So, here, first of all, I want to change something. In this instance, to make it match your book, we're going to say delta Q, delta U. Okay? So, here, if Q is positive, it means that the system gained the heat and the surroundings lost it. If it's negative, it means the system loses heat to the surroundings. Likewise, if W is positive, it means work is being done on the system and the surroundings is doing the work. Whereas if W is negative, it means the system is doing the work on the surroundings. Overall, if delta U is positive, it means that it is endergonic and that there's a net gain of energy by the system. If it's negative, if delta U is less than 0, it means that the system has lost energy to the surroundings. So let's just do an example here. Okay, so in this instance, don't judge me because of my artistic abilities, please, but I've drawn a system here where we have two gases, A and B, that are being forced by a piston in order to make a solid C. Okay? So as this reaction occurs, the system actually loses 1150 joules of heat to the surrounding. The piston will move down to form the solid, but as the volume of gas decreases under constant pressure, the surroundings does 480 joules of work on the system. So what is the change in the internal energy of the system? Well, we know that delta U is equal to Q plus W. So delta U, we have to figure out what the Q is. Well, the Q has to do with heat. It says that the system is losing the heat, so it's going to be negative 1150. Oops, this was supposed to be a 50, but it kind of got chopped off. So that means we're going to have negative 1150 joules. You always want to make sure that the units are the same, because sometimes they'll do 1 in joules, 1 in kilojoules, or 1 in calories and 1 in joules, plus work. Now here, I just want to show, it says the surroundings do 480 joules of work on the system. So since the work is being done on the system, it's positive. So it's plus a positive 480 joules. So the delta U overall, the internal energy for the system, it's important that this is for the system, we would just have negative 1150 plus 480, and we get negative 670 joules. So is this an endergonic or an exergonic system? This is an exergonic reaction because the system is losing energy overall. It's being given off. And we know that because of the fact that, let me get to the color. You can see that this sign right here is negative. So it's exergonic. Let's do another example. Here we want to calculate the internal energy of a system for a process in which the system absorbs 140 joules of heat from the surrounding and does 85 joules of work on the surroundings. So once again, let's just write our equation, which is delta U is equal to Q plus W. And we need to figure out what is Q and the sign and what is W. Well, so we have 140 joules of heat. But we need to know, is that positive or negative? Since it says the system absorbs it, that means it's being added to. So Q is equal to a positive 140 joules. Now let's think about work. It says that the system does 85 joules, of work on the surroundings. So we know it's an 85 joules. Was it positive or negative here? Since the system is doing it, that means it's giving up, or it has to do the work. If you want to think of this as a bank and money, we had 140 joules of heat added in, but we had to take 85 of it out. And so we're going to have delta U is equal to a positive 140 joules plus a negative 85 joules. So delta U is equal to, you'd have 140 minus 85, and you're going to get 55, and it's a positive 55 joules. So this is an endergonic or an exergonic system. This one would be endergonic because it's a positive number. It's greater than 0. I hope that this has helped talk a little bit about the transfer of energy between two objects and how it can be transferred between them in the form of either heat and or work. And then the next video we'll talk about enthalpy and how enthalpy is related to this process.